news, bad news. Bad news is there's a lot of stuff on the final exam, and there's no way I can cover an entire semester in 2 hours. Good news, I'm going to go over the topics that you need to go over, and luckily, we've had 3 exam reviews already that are all recorded already that go into more detail about the things that I will highlight today, okay? So, if you've been following along with the reviews previously, you may recognize a lot of these topics, and everything is still on YouTube, and I'll resend all those links out so you guys can watch them over again, because I'm sure you guys aren't tired of my voice yet. So, alright, we're going to start with Chapter 1 and Chapter 2. So, I will not be writing much today, especially because the camera sucks, so I'm just going to highlight the topics via PowerPoint. I'm going to point out things that you guys should really be focusing on, and especially anything that involves solving, we've gone over in detail throughout the semester. I will highlight those things, and it's up to you to go back and look at the details on how to solve these certain things. Okay? So, starting with Exam 1 and 2 material, Exam 1 material, Chapter 1 and Chapter 2. Chapter 1 is the very introduction to biochemistry. Chapter 2 is a little bit of general chemistry topics. What you need to know, and I believe I can jump to this slide to illustrate, is your weak intermolecular forces. All right, your weak intermolecular forces. And let me make sure this is recording because that would suck if it wasn't. Okay, everything's recorded. All right. Weak intermolecular forces. If you're given a molecule, you need to be able to identify what intermolecular force is likely to be affecting that molecule. So water, obviously, is going to be affected by what weak intermolecular force? Hydrogen bonds, right? Any molecule that can be given, it'll be very simple looking molecules. You've seen them on Exam 1. Simple molecule, what intermolecular force is dominating it? That's one thing you need to know. The other thing with intermolecular forces is the relative strengths of them compared to each other. I said it a long time ago, but I'll highlight it again here. For this class, ionic bonds are the strongest type of bond. Okay, so ionic bonds are the strongest. Second place is covalent bonds for this class. So ionic, then covalent, then hydrogen bonds. Okay, ionic, covalent, and hydrogen bonds. And then you get to your weaker forces, such as dipole-dipole, and the weakest one, London dispersion, which can also be called van der Waals. All right? Those are from strongest to weakest. You may be given a question where they give you a bunch of different molecules and they'll ask you to order them from strongest to weakest or weakest to strongest, whatever order, all right? So, a little bit of a refresher there. Other stuff you need, oh, and by the way, because we don't have a lot of time, and because someone's using the room after us, I will not have time to answer questions during the review. I will stick around afterwards somewhere out there. We can go in the lawn there, and if anyone wants to ask me questions, I will answer them then. Okay, so other stuff that you need. And we practice this also. I will not be able to go over it in detail. Be able to calculate the enthalpy of formation given a reaction. You have a couple examples in the practice exam. You have examples at SI, and we went over some in detail during the first exam review. Please refer to that. You may be given a reaction. You will be given the numbers that you would usually find in this table. You'll be given the numbers, and you have to calculate the enthalpy of formation either for the reaction as a whole, and you can remind yourselves that if it asks you for the entire reaction, you just calculate enthalpy of formation like we learned. I may say some things that don't sound familiar to you right now. When you review, you will recognize them. Some tips for enthalpy of formation. You want to calculate reactants minus products. It sounds backwards, but you can review the notes. I have said this before. An oversimplification of the process is to calculate enthalpy of reactants minus enthalpy of products. Okay, that'll give you your enthalpy of formation of the reaction. What if it says enthalpy of formation per mole of product, per mole of H2O or something, per mole of product? What do you do then? You have to divide by the coefficient. Exactly. Some of you remember, and others, if you don't, you will see it. I tell you that during the Exam 1 review. You must divide by the coefficient in front of that product or that reactant. So read the question carefully to see if it's asking for per mole of something or of the whole reaction. All right, other stuff. jumping around on accident some. I don't remember. Okay. All right. Chapter 2. Hydrophobic interactions. Hydrophobic interactions. A nice, simplified way of understanding what hydrophobic interactions are is the interaction between two hydrophobic molecules. What determines if a molecule is hydrophobic? Well, the one example that we know in detail and may show up on the exam are nonpolar amino acids, right? You do have to know your amino acids, and I will reiterate that when we get to chapter 4 in a second. But you know that there's a category of amino acids called nonpolar amino acids. Nonpolar amino acids will interact with each other through something called hydrophobic interactions. All right? Nonpolar stuff loves to interact with nonpolar stuff. Polar stuff loves to interact with polar stuff. You may have also learned that there's a category of molecules called amphiphilic molecules, or also known as amphipathic molecules. These are molecules that have both polar properties and nonpolar properties. We learned that depending on what type of amphiphilic molecule you have, you may form something called a micelle, like this, or a liposome, like this down here. The one feature we learned that determines whether you form a micelle or a liposome is looking at the number of tails in your particular phospholipid. Anyone want to remind me, how many tails must your phospholipid have if it's going to form a liposome? 2 tails. Good. Along. Formulas and stuff, all these acid-base formula stuff. The most important ones, and unfortunately they are scattered here, so I will try to find them here for you. One important formula you need to know is this one right here. pKa plus pKb equals 14. You may be given pKa or you may be given pKb and you're asked to calculate the remaining things. Okay? Very simple. Yes, you need a calculator for the final exam. You will get calculation questions. We do not have calculators. Please bring a calculator. Please bring a calculator. Please bring a calculator. Scientific calculators only, and if you don't have one, good luck. All right. It happens every exam. Okay. Again, sorry if I'm going a little bit out of order. I will be jumping around. Henderson-Hasselbalch equation. You may be relieved to know you won't have to do any really complicated calculations with Henderson-Hasselbalch equation. You just need to know general properties. When would you use the Henderson-Hasselbalch equation? For what types of acids? Only weak acids. Henderson-Hasselbalch equation you can only use for weak acids and their conjugate bases. There's also a nice quirk with the Henderson-Hasselbalch equation. What happens if your concentration of weak acid and concentration of conjugate base are equal to each other? Well, mathematically, the numerator and denominator will equal to each other, so you end up with log of 1, which equals 0. So the quirk here is that when the weak acid concentration equals the conjugate base concentration, pH is going to be equal to pKa, right? That's about the extent of Henderson-Hasselbalch calculation that you're going to need, and it isn't even really a calculation, so you'd be relieved to know that. Okay. Other formulas that you need, I may have passed it already. This one right here, you need to be able to know how to calculate pKa if you're given Ka. All right, pKa, the formula is right here. pKa equals negative log of Ka. Very similar to the pH formula. So make sure you know how to use that. Make sure you know the formula. I believe at the very end of this, they talk about buffers. Buffers are those weak acids and their conjugate bases whose main job is to resist changes in pH. There are some properties of buffers we have to worry about, such as enzymes prefer a particular pH to operate in. So if we wanted to, and you might remember this topic on exam 1, so if you wanted to pick a buffer that is ideal for a particular enzyme, what property do you need to find? You need to find a buffer whose pKa is equal to the enzyme's optimal pH. All right, if you don't know what any of that means, that has been detailed in the exam 1 review, you can find that there. You need to find the buffer whose pKa is equal to the optimum pH. You may be given something that looks like that, a graph that shows different enzymatic activities based off different pHs. You may notice that some enzymes prefer higher pHs, some enzymes prefer lower pHs. You may be asked which enzyme prefers the environment of the stomach. What type of environment is the stomach, acidic or basic?
Acidic.
Acidic. If you're given a graph like this, could you find what enzyme prefers the stomach? What about the duodenum, which is adjacent to the stomach? That one has a higher pH, right? If you're asked what enzyme prefers the duodenum or is most preferred, because you'll have several options here, you want the one who prefers the highest pH. All right. Again, you can save your questions for afterwards. I will be out there. We can talk out there. All right. I think that is everything. Oh, what property of a buffer determines if it's a strong or weak buffer? Anyone remember? It is molarity, concentration. The more buffer you have, i.e. the higher the concentration, the stronger the buffer. The less molarity you have, the less concentration, the weaker the buffer.
You said the higher the molarity, the higher the buffer.
Higher concentration, stronger buffer, yes. Okay, I think that's it for chapters 1 and 2. We are running against the clock here, so moving on to chapter 4. All right, chapter 4, amino acids. Yes, you need to know the side chains of your 20 amino acids. However, this is a multiple choice exam. And just like with exam 1, you don't need to know every single carbon and every single hydrogen and every single nitrogen and blah, blah, blah. Be able to identify the amino acids from each other. So just know to the level that you can pick one out from another given pictures. All right? Most importantly, though, is knowing which amino acids belong in which category of amino acids. So there's 4 categories we use in this class: polar amino acids, nonpolar amino acids, acidic amino acids, and basic amino acids. A lot of questions can be answered simply by knowing what category of amino acid you are dealing with. Not to give any specific details, but that's a good thing to study, is the different categories of amino acids. So what amino acids go into which category. All right. I will not be able to go over this in detail here, but I have gone over it in extreme detail before. You may be asked to determine the charge of a peptide given a particular pH. So if you're given a peptide that's like 4 or 5 amino acid sequences long, and you're told you're at a pH of 13, what charge does this peptide have? I have gone over that in detail during the exam 1 review, so please refer to that. Other type of determination type things. Determine the isoelectric point of a peptide given the peptide sequence. All right, I've gone over that. There are these tricks, and I've taught you guys how to make certain things called charge diagrams to help you answer these things. Please refer to those things. And not only will you have to determine the charge of a whole peptide given a pH, but also determine the charge that a given amino acid may have at a particular pH, which is easier than figuring it out for a whole peptide. So charges of stuff, charges of peptides at certain pHs, charges of amino acids at certain pHs, and be able to calculate the isoelectric point of a given peptide. Okay. Some of these topics I may not have remembered exactly what chapter it's found in, so forgive me if I'm on the wrong chapter when I talk about a particular topic. Chapter 5, the main component of chapter 5 was sequencing amino acid sequences, so sequencing proteins, right? we learned in exam 1 that the extra credit question was you had to sequence like a pentapeptide, right? There is no extra credit question on the final exam, it's all multiple choice, but you may be given a question that gives you a list of clues, and you have to figure out what the original amino acid sequence was from that list of clues. Those clues will include things like, I use trypsin, and it results in a dipeptide and a tripeptide. That's one clue. Sounds familiar, right? I use Edmonds Reagent, and it gives me phenylalanine, right? If you don't remember what any of those are, go review exam 1. There are ways to solve these things. It's easier for the final exam because it's multiple choice, so you can narrow down your answer choices based off which answer choices fit the clues. Speaking of those clues, remember that you will be given the table. Don't worry, you don't have to memorize what trypsin targets, what cyanogen bromide targets or anything. You will be given that table. You do have to know, though, what part of the amino acid each of those cleaving enzymes target. I use the phrase, the C side of an amino acid. You can go remind yourselves specifically what that looks like, but a short explanation is, trypsin targets the C side of lysine and arginine. You go draw lysine and arginine, the C side of any amino acid, does anyone remember, is which side, the left or the right side?
Right.
The right side, okay? So when we talk about those cleavage enzymes, they're always targeting the right side of a particular target that is given, all right? The only kind of enzyme chemical thing you have to know, because it won't be given in the table, is Edmonds reagent. Remember that Edmonds reagent is a thing that tells you the first amino acid in a particular sequence. And then there's another thing called carboxypeptidase, which tells you what? The last amino acid in a sequence. All right, so if you see any of those clues, make sure you remind yourself. So it's Edmonds tells you the first amino acid, carboxypeptidase tells you the last amino acid. Everything else is given to you in a table, and they will target the C side of particular amino acids. All right, gotta move on. Okay, I think it's in this chapter. Or maybe it's not in this chapter. One second. Cannot recall what chapter is in. One of these chapters, they talk about a method of separating mixtures of amino acid sequences. You have to find it yourself, but they talk about something like cation exchange column, anion exchange column, really complicated sounding names. I went over this during the exam 1 review, but I told you that it can be simplified to separate your amino acids either based off increasing pH or decreasing pH. So go review to figure out how to do that.
It's chapter 4.
It is it's one. I couldn't find it in there, but you can find it in chapter 4, and most likely it is better for you to go look at the SI worksheets and review how to answer those. It is simpler than it sounds. It is literally just separating mixtures of amino acids based off increasing or decreasing pH. Okay. There's not really a good picture of this thing. Remember how I said that it is very important for you guys to know the classifications of your amino acids, right? Acidic amino acids, such as aspartic acid, are generally going to be what charge at neutral pH. And remember, they can be positively charged, negatively charged, or neutrally charged at neutral pH. Acidic amino acids will be negatively charged. Okay, you can review that. That's a bit of a shortcut, is that acidic amino acids will be negatively charged at neutral pH. Anyone want to guess about basic amino acids? Positively charged, okay? Those two features allow you to also separate amino acids on a gel, performing gel electrophoresis, right? Remember that those gels separate DNA, separate proteins, they separate everything based off some property, okay? For proteins, what we use it for is separate, to oversimplify, we separate proteins and amino acid sequences based off their charges. So you may get a gel where they label what side of the gel is the positively charged side and what side of the gel is negatively charged. And you will get lines on that gel, and you have to figure out which lines represent an acidic amino acid, which line represents a basic amino acid. Okay? I believe the similar example we talked about in exam 1 was some disease, right? It was like cystic fibrosis or Tay-Sachs disease, some disease. We were given a gel, and we had to figure out which sample on there represents someone with the disease and someone without the disease. I've reviewed that previously. You can take a look at the notes about that. All right. All right. So this one, I believe, is at the end over here. Okay. Different levels of protein structure. You have primary, secondary, tertiary, and quaternary. Know the general features of each one. Primary structure of protein is the easiest one. That is simply an amino acid sequence. Secondary structure, we learned of 2 types, alpha helices and beta sheets. We have 1 or 2 slides devoted to each one of those. Let me find the alpha helix one. We have a few slides devoted to each one, and there's a few properties of each one you should know about. Know the properties of the alpha helix, such as you are not going to find a lot of prolines in alpha helices because prolines are known as helix breakers. And, oh yeah, this N and N+4 rule. If you don't know what that is, you can review the exam 1 review. All right, features of alpha helices. Same thing with beta sheets. You don't have to memorize these numbers for alpha helices. Don't worry about that. I'm talking about general structural features of alpha helices. Let me go down to beta sheets. Beta sheets even simpler. There's barely information we were given about beta sheets. Beta sheets, we just know that there's 2 types. There's either parallel or anti-parallel. You don't have to memorize these numbers associated with it, just general features of beta sheets. Okay, I do not know what chapter the following is, but there are certain phrases. It actually might be 6B, so let me actually jump to that first. It might be there. Yeah, no, it isn't here. All right, so we learned about in later chapters things called multimeric proteins. These are proteins made of multiple subunits. To give you a detailed one, we learned in chapter 28 there is an enzyme called DNA polymerase 3, right? That enzyme is responsible for replicating DNA in prokaryotes. It is composed of several subunits, an alpha subunit, a beta subunit, epsilon, theta subunits. It's composed of several subunits. Any protein that is composed of several subunits is called a multimeric protein. Okay? Each subunit is an individual amino acid sequence. Each subunit is an individual, separate amino acid sequence that had to fold into a 3-dimensional shape. For 6B, the most important tertiary structure you should learn about and study is collagen, the features of collagen, right? Especially the sequence features of collagen, some of which are listed here, such as it's the one tertiary structure you've learned about that actually has quite a lot of proline in it. It has some special amino acids in it. These are features of collagen you should familiarize yourself with. It's the most important tertiary structure we learned in this class, and you may be asked about it. Okay. I know I'm going fast. Obviously, if for whatever lucky reason, if we happen to finish early, I will go back and I'll talk about certain specific things. Okay. All right, exam 2 material. Exam 2 material started with enzyme kinetics, then went into sugars, then went into lipids, right? And also somewhere in there is regulating enzyme activity. So to begin with enzyme kinetics, there is lots of formulas and graphs on here, and you know we don't want to ask you everything, so we focused mostly on the most important graph in enzyme kinetics. Eventually I'll get to it. Is the Lineweaver-Burk plot. you guys might remember, and if not, go review, how to find Vmax and Km out of a Lineweaver-Burk plot, okay? How to find Vmax and Km out of a Lineweaver-Burk plot. If you guys don't remember what Vmax or Km are, Vmax, the name is pretty intuitive. It's the maximum speed that an enzyme can operate at. And Km is a number that describes how well an enzyme binds to a particular substrate. A lower Km value indicates that the enzyme binds to its substrate very strongly. So little hints and stuff like that. All right, I'm not going to cover this. You got to practice how to calculate certain things. All right. One other one, let's see, is this special value called Kcat. All right, make sure you know how to calculate Kcat. Oh, look at that, they give you the formula right here, so make sure you know the formula for it. It is also known as turnover number. Kcat, you can think of it conceptually as the maximum speed of a single copy of an enzyme, not a group of enzymes. Kcat is the maximum speed of a single copy of an enzyme. You can quickly calculate that by finding Vmax through whatever means that we talked about earlier, and divide it by the concentration of enzyme, which would have to be given to you. All right? That is up to you guys to learn how to do that. We learned about different inhibitors. Of enzymes. There's competitive inhibitors, which go where on the enzyme? What site do competitive inhibitors go to on the enzyme? Active site. Non-competitive inhibitors go where instead? Allosteric sites. They go to not active site. Okay? All right. Okay, the most important topic that you need to study in 13b/15 is allosteric enzymes. So let me go down to allosteric enzymes. Allosteric enzymes. These are different than the enzymes talked about in 13a. The enzymes talked about in 13a are what are called Michaelis-Menten enzymes. They operate via Michaelis-Menten kinetics. Allosteric enzymes are highly regulated enzymes. They are either 100% active, they are either fully activated or fully deactivated. Kinetically, that is described with this phrase here, the sigmoid shape. You notice how there's a flat line at the top here and also a flat line at the bottom there. That's to indicate that an allosteric enzyme can be switched on or switched off. That act of switching on and off is illustrated on a diagram such as this one. Allosteric enzymes have the ability to be in two different states, a relaxed state or a tense state. And you see synonyms for that. The relaxed state is also known as the active form of the enzyme. The tense state is also known as the inactive form of the enzyme. There are certain molecules and substrates and effectors that will shift equilibrium in one direction or the other, that will turn allosteric enzymes on or turn them off based off just being present. An example is substrate. If a substrate is present, it's going to turn on allosteric enzymes by causing equilibrium to shift to the right. You can review the exam 2 review to give where I illustrate that in more detail. But in general, a substrate will activate an allosteric enzyme by shifting equilibrium to the right here. Inhibitors, the logic is pretty sensible. Inhibitors are going to shift equilibrium to the left, to the inactive form of an allosteric enzyme. And depending on what effectors you have, some bind to the active site and some bind to allosteric sites on an allosteric enzyme. And we come up with terms to describe those. Homotropic, and I'm going to say it quickly, homotropic is the word we use to describe effector molecules that bind to the active site of an allosteric enzyme. And heterotropic is the word we use to describe effector molecules that bind to allosteric sites on an allosteric enzyme. And this is recorded so you can hear me say that over and over again when you're watching it on YouTube later. Okay. Here's the feedback. No, not here. Oh. It wasn't asked about on exam 2, but I did mention that if it wasn't asked about on exam 2, it may be asked about on the final exam. And that is this interesting fact here about epinephrine. Actually, this might not be the right slide for it, so excuse me. Epinephrine is a hormone that activates the breakdown of glycogen. Epinephrine is a hormone that activates the breakdown of glycogen. One way you can probably think of this is we learned about an enzyme called glycogen phosphorylase that is super activated in situations of flight or fight, right? We remember there's an emergency release of glycogen that occurs in a flight or fight response, right? And that's glycogen phosphorylase is breaking down glycogen into glucose at a really fast rate. That response is activated by the stress hormone epinephrine, all right? Which is detailed somewhere on here. I'm summarizing it for you here instead. Okay, earlier, metabolic pathways, all right? We've gone over an example during SI and during the reviews about metabolic pathways. And I gave you an example that was a branched pathway, right? I won't illustrate it up here, but you may be given a branched metabolic pathway, given some detail about something inhibits something else in that pathway, and your job is to figure out what happens when that inhibition happens. So, for example, remember that in a metabolic pathway that divides into two different pathways, one pathway gets shut off, and the second pathway is super activated. How does that happen? Go review the exam 2 stuff. I illustrate that for you. All right, moving right along. Have you scared yet? All right. I was surprised too by how much is in this class. So, I've done this enough that it may not sound like that. Okay. 7A, monosaccharides. Just like for exam 2, there's a small number of monosaccharides you need to know, and you need to know the cyclic form of them. So I will jump down to this slide. Glucose, make sure you know structurally. You may be given a picture of one of these monosaccharides and you have to say what it is. Glucose is the easiest one because you go look at its functional groups and they're all alternating, right? Up, down, blah, blah, blah. There's also 3 other monosaccharides that look very similar to glucose. Dr. Hayes comes up with an acronym called GALOMAN, galactose, allose, and mannose. Compare each one to glucose to help you memorize the structures of galactose, allose, and mannose. They differ at only one chiral center. So that's 4 of the monosaccharides you need to know. There are 2 others not illustrated on this slide, and I can't remember which slide it is. That is fructose and ribose. You must also know those structural, the structure of those monosaccharides, fructose and ribose. Let me see. There's a good slide that illustrates the following. Probably not. There isn't a good slide that illustrates the following property, but remember that there are 2 categories of sugar, 2 enantiomers of sugars that exist. D sugars and L sugars. Which one is the more common one in nature? D sugars. What carbon, if given a picture of a cyclic monosaccharide, what carbon possibly determines the chirality, whether it's D or L configuration? Let me pull up a cyclic one here. I gave you a nice shortcut when we were reviewing exam 2. The shortcut was the second highest numbered carbon is the one that determines whether you have the D or the L configuration in sugar. So for example, in glucose, where would you find the second highest numbered carbon? Right here, right under CH2OH. What happens if it's fructose? You have to figure it out for fructose. What happens if it's ribose? You have to figure it out for ribose. The shortcut is the second highest numbered carbon in any of those structures will tell you whether you have the D configuration or L configuration. You will not be required to identify whether you have D configuration or L configuration, because that's complicated, but you need to tell me which carbon is likely the one that tells you whether you have D or L configuration. All right, moving along. So you see these squiggly lines, right? That was one notation to help describe a special carbon in monosaccharides and disaccharides and polysaccharides called an anomeric carbon, a free anomeric carbon. If you're given either a monosaccharide, disaccharide, or polysaccharide, you may need to know which carbon is the free anomeric carbon. Quick way of identifying that is two things that you look for. One, an anomeric carbon, whether free or not, is one bound to two oxygens. So that's pretty easy. You see this example right here with glucose. You look at the right carbon right there. It's the only one in the entire picture bound to two oxygens. A free anomeric carbon is one in which there is a hydroxyl there somewhere. There has to be a hydroxyl, an OH group attached to that anomeric carbon. And with it, if you identify if a particular carbon is a free anomeric carbon, there's a bunch of extra things we usually attach to that, such as a free anomeric carbon has the ability to undergo butarotation, right? That sounds familiar, switching from alpha anomer to beta anomer. And there's some other properties, such as any sugar that has a free anomeric carbon can also be called a reducing sugar. That might also sound familiar. So if a given disaccharide or polysaccharide drawn for you does not contain a free anomeric carbon, can it be a reducing sugar? No, if there's no free anomeric carbon, it can't be a reducing sugar. You may be given a disaccharide. It may not be any of the ones on here. You'll be asked, just like how we reviewed for exam 2, how to give the full name of that disaccharide, which is pretty easy. You only have to do a couple things. If you're given a disaccharide, even one you've never seen before, you just have to identify the two monosaccharides that are involved, what type of linkage connects them, whether alpha or beta, and what numbered carbons the linkage is between those two monosaccharides. We reviewed that during exam 2, so you can look at that for additional details. But you may be given a disaccharide and may be asked to give the full name. It may not be any disaccharide on any of these slides. You're still able to answer it because you know your monosaccharides, and you know how to identify alpha versus beta link, and you know how to identify carbon numbers when you go look at previous reviews in detail. Okay, really, is that it? All right, let's see. Okay, 7b talks about polysaccharides, of which the most important one that you may need for the final are your glycoproteins, of which there's two categories, O-linked and N-linked glycoproteins, and each one has slightly different properties with each other, right? You learn that glycoproteins are proteins that have a sugar attached to it. And this sugar is associated with these proteins via 3 possible amino acids, of which I will not remember right now. Let's see. O-linked glycoproteins, you can see it on the slides here, associate with sugars via serine and threonine amino acids. And N-linked glycoproteins the protein associates with sugars via the asparagine amino acid. Additionally, N-linked glycoproteins come in 3 flavors: high mannose, complex, and hybrid, each of which is actually pretty easy to identify because they're so complicated they don't look anything like each other. So if you're given any one of these, you may be asked to describe what category of N-linked glycoprotein you have there. So take a look at this. It's my opinion, the easiest one to identify is high mannose because it's in the name, it just has a bunch of mannose sugars in it.